Welcome to MRS Bulletin's Materials News podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Laura Lay. The natural world has developed some sophisticated structures and mechanisms. The scales of an ancient fish, once thought to be extinct, exhibit excellent fracture toughness. Probing the mechanism behind this fracture toughness enables improved concrete structures to be developed using advanced additive manufacturing.
The materials and the structures that we will design in the next 10, 20, 30 years won't be the same as the ones we design today. So the meaning of concrete may change in almost every aspect we know today, given the advanced manufacturing capabilities, but also advanced computational and design capabilities that are only going to grow. In other words, as we advance our tools of design, computation, and fabrication, we may be redefining what concrete is as a material and what properties it can be bestowed upon in the future that may be strange today.
That was Dr. Reza Moini, Assistant Professor of Civil and Environmental Engineering at Princeton University. Fish scales are comprised of bundles of collagen known as fibrils that produce sheets or lamella. In most fish, each lamella is rotated relative to the one they are adjacent to, forming a simple helical structure. The fish scales that inspired the work on concrete are different. They have a unique double helical or double Bouligam structure.
In the silicon fish scale, the fiber bundles in the adjacent two layers form an orthogonal bilayer as one unit. These orthogonal bilayer units then progressively rotate through the whole thickness of the scale, known as double helical architecture. Between these fiber bundles also exist interbundle fibril arrangements that are more loosely packed, leading to the presence of a weak interface between the fiber bundles.
The double helical structure, together with the soft interface between the hard lamella, lead to a structure with improved resistance to deformation, including resistance to delamination of the lamella. Compared to traditional formable materials such as cement and concrete, which have limited ability to dissipate energy at the microstructural level, the structures in the fish scale lead to enhanced fracture toughness. Applying the same architecture to concrete, the bilayer appears to promote crack shielding, and this, along with interlocking behind the crack tip as well as deflection ahead of the crack tip, lead to enhanced fracture toughness compared to cast counterparts. In order to apply the same structural motifs to concrete, Dr. Moini's team needed to develop an enhanced additive manufacturing technique. They used a two-component extrusion system where a concrete mix of cement paste and fine aggregate was dosed with an accelerant to control the curing process. The extruder was manipulated using a robot arm and controlled using specialist algorithms. These sorts of developments take time, perseverance, and inspiration. Often they only move forward after an unintentional discovery, as Dr. Moini explains.
The unknown that we stumble upon, sometimes in the lab due to an accident, due to an error in the experiment, which then reveals questions to us that we have not been asking. We're always fascinated and surprised by coming across one of those, which don't necessarily happen every day. It is important to allow the researchers to have some time, to carve out some time to explore and be ready to be surprised, and allow for some time to treat the research and the science as a playground, and not only do formalized research, but allow for some ability and some time to facilitate discoveries.
This work was published in a recent issue of Nature Communications. My name is Laura Lay from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org. Follow us on Twitter at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.